Introduction. Two forms of application where ordinary differential equation were used, namely population growth and decay, and Newton's law cooling, will be explored in this chapter. First, growth and population. The increase in the number of people in a population is known as population growth. The rate of population increase is proportional to the number of people in the country. It is the change in a population through time, and it may be quantified as the change in the number of individuals of any species in a population measured in per unit time. The formula of growth and population is P of t is equal to P0 exponential the power of kt. P of t is the number of population for any time. P0 is the initial number of population. E for exponential. K is the proportional number for any constant. T is the number of any time. Next is Newton's law of cooling. It is a mathematical model that explains how an object temperature changes in a particular environment. The law states that the rate of change in time of the temperature is proportional to the difference between the object's temperature and the temperature of the environment. The formula of Newton's law of cooling is T of t is equal to Te plus T0 minus Te exponential the power of negative kt. T of t is the number of temperature for any time. Te is the environment numbers of temperature. T0 is the initial number of temperature. E is exponential. K is the proportional number for any constant. T is the number of any time.
Hi, Assalamualaikum. My name is Nur Nabila binti Ruslan and my matrix number is AA20908. Okay, so now I want to explain about filler table for the part A, which is we got question number 6. So for the fact, first, the question is about the increasing of the population of insect. Second, the beginning of the population of the insect is S. And third, the population of the insect after 10 days is S to the power of 2. Fourth, a student find the population of insect after 5 days. Fifth, a student calculate the days taken for the population of insect to be 3 times the original. Okay, so for the ideas, first, use growth and population. Second, use another related formula to solve the equation. 3, jot down and highlight all the information given. And fourth, try to think and imagine the situation logically. Okay, so for the learning issue, first, which topic must we learn to solve the equation? And next, what kind of formula needs to be used in the equation? Next, what kind of calculation technique is suitable to solve the equation? And lastly, which keyword must be highlighted in the equation to solve the equation? Okay, so for the resources that we use, first, notes given by our madam, which is Madam Rabi'ah binti Adam. And second is YouTube channel, which is from Madam Rabi'ah binti Adam. Okay, so next, filler table part B. Part B, we got question number 6 also. So, for the fact, first, the body temperature is count by the Newton law of cooling states. Second, a body temperature at 80 degrees Celsius is placed in a room that is 15 degrees Celsius. Third, 15 minutes is take for temperature to reduce to 60 degrees Celsius. 4, find the temperature of the body after another 10 minutes. 5, find the time taken for the body to reduce its temperature from 60 degrees Celsius to 20 degrees Celsius. Okay, next for the ideas. First, use Newton's law of cooling. Second, use another related formula to solve the equation. Third, jot down and highlight all the information given. And fourth, try to think and imagine that situation logically. Okay, so for the learning issue, first, which topic must we learn to solve the equation? Next, what kind of formula needs to be used in the equation? Third, what kind of calculation technique is suitable to solve the equation? And lastly, which keyword must be highlighted in the equation to solve the equation? Okay, so for the resources, we use notes and YouTube that given by our madam, which is Madam Rabi'ah binti Adam. That's all from me. I will pass the presentation to the next presenter. Thank you.
Hi, my name is Akila Nabiha binti Abdullah. My matric number is AA200073. For question 6, part A, the rate of increase of the population of insects is proportional to the number P of insects present at any time, days after the beginning of the experiment. Given that the population of the insects at the beginning is S and after 10 days is S2, find in terms of S. So, the question asks us to find the population of insects after 5 days and the days taken for the population of insects to be 3 times the original.
So for solution A, the population of insect after 5 days, we use the formula P equal to P naught exponent to the power of KT, P equal to S, T equal to 0, and we get P0 equal to S exponent K is 0. And next, if P equal to S the power of 2 and T is 10 and S exponent to 2, we equal with S exponent the power of K 10. And we get S exponent S the power of 2 divided to S equal to exponent 10k, and S we get S equal to exponent 10k, and we get ln S equal to ln exponent 10k, and we get k is equal to ln S divided to 10. And next we want to find the P of time t, and the time 5 is a 5, and the P we don't know, and P5 equal to S exponent the power of ln S divided to 10 and multiply with 5, and that's the equation. And then after that we gonna solution of P, the days taken for the population of insect to be 3 times the original, means 3S equal to S exponent the power of ln S divided to 10 multiply with T, we don't know T, and 3S divided to S equal to S exponent the power of ln S divided 10 and multiply with T, and we get 3 equal to exponent the power of ln S divided to 10 and multiply with 10 with T, ln, and we get ln 3 equal to ln 5 divided to 10 to multiply with T, and we get T ln 3 divide the ln S divided to 10, and we get the equation of T is 10 ln 3 minus 5 in bracket.
For question 6, part B, Newton's law of cooling states that the rate of decrease of temperature of a hot body is proportional to the difference in temperature between the body and its surrounding. A body at a temperature of 80 degrees Celsius is placed in a room whose temperature is 15 degrees Celsius, and it takes 15 minutes for the temperature to reduce to 60 degrees Celsius. So, the question asks us to find the temperature of the body after another 10 minutes and the time taken for the body to reduce its temperature from 60 degrees Celsius to 20 degrees Celsius.
So for the solution, we get the T naught equal to 18 degrees Celsius, T environment we get 15 degrees Celsius, and the T15 we get 60 degrees Celsius, and T10 we don't know the temperature. So A, the temperature of the body after another 10 minutes, we will find that the 10 minutes, so we use the formula T equals to T environment plus in the bracket T naught, we minus with the environment, and we multiply with exponent the power of KT. So so the 60 equal 50 plus in the bracket 18 minus 15, we multiply with exponent the power of K in the bracket is 15. So so we get the negative 65 exponent negative 50k equal to negative 45, is a 45, and exponent negative 50k we get equal to 9 divided to 30, and we get ln exponent negative 1.5. I'm sorry, it's a ln exponent negative 5k, and is equal to ln 9 in bracket 9 divided to 13, and we get the negative 50k equal to 0.3677. When we calculate the ln in bracket 9 divided to 13, we get 0.3677, and the k is, we get the k is 0.0245 when we calculate that. So we can get the 10 minutes, the temperature of 10 minutes. We can use the same formula, and we just change the time. So T10 equal to 50 is plus in bracket 18 minus 15, just like before this, before this. So the exponent, we get the power of 0.0245. We multiply with 10. So we get the answer is 65.9 degrees Celsius. The solution of part B is the time taken for the body to reduce its temperature from 60 degrees Celsius to 20 degrees Celsius. And we get the new equation is T equal to 15 plus 65 multiplied with exponent, the power of negative 0.0245 T divided to T. So we get 20 equal to 5 equal to 50 plus 65 exponent, the power of negative in bracket the multiply of 0.024550, and we get exponent negative 0.0245 T, and we equal that with negative 0.0769, and we get ln exponent negative we get ln 0.0796, and we equal that with the negative 0.0245 T ln exponent, and we get T equal to ln 0.0769 divide to negative 0.0245, and we get T equal to 104.07040 equal to 60, and we get the minutes, and when we calculate that, we get the minutes that 1.75 minutes. That's all.
Assalamualaikum warahmatullahi wabarakatuh. My name is Nur Farah Wahida binti Ismail. My metric number is AA200282. Today I will present about discussion and conclusion. Part A, question 6. The discussion for question 6, part A, can be solved using growth and population formula. Pt equal to P0 exponent square KT. Equation of growth model. For this question, P0 equal to S, which is referring to the population of insect at the beginning. Then, S squared 2 is the population of insect after 10th day. As a conclusion for the solution and result we calculate, we can conclude that the population of insect after 5th day is P5 equal to S exponent square ln S over 10 times 5. And the days taken for the population of insect to be 3 times the original is 10 ln 3 minus S equal to T. Next, part B, question 6. The discussion for the question 6 part B can be solved using Newton's law of cooling formula. Tt equal to T environment plus A exponent square negative KT. For this question, T0 equal to 80 degrees Celsius, which is referring to the cooling process starting. T environment equal to 15 degrees Celsius, referring to the environment temperature, and T15 equal to 60 degrees Celsius, referring to the temperature after 15 minutes cooling process. As a conclusion for the solution and result we calculate, we can conclude that the temperature of the body after another 50 minutes is T10 equal to 65.9 degrees Celsius, and the time taken for the body to reduce its temperature from 60 degrees Celsius to 20 degrees Celsius is T equal to 1.05 minutes.